So, in the last lecture we discussed about the shear flow examples. So, we did one example where the box section or the let us say the channel section with an overhang or a drop hang here for a dimension of 40, 13, 120 made a shear flow diagram like this, and then we computed the shear center to be around 12.82 millimeters. So, there is a small correction which I want you to do. The shear flow pattern is what we have marked here, which is as same as what we discussed in the last lecture. The shear flow or the force here at the center was computed to be 113 in my last lecture. It was actually 72.84. There was a small calculation mistake. So, thanks for pointing it out. It will be 72.84, it is not 113. So, in this lecture we will talk about the plastic capacitive sections under different combination of loads. So far we have been seeing that when a specific kind of load is acting, maybe axial tension or bending etc., we are able to see that the stress reaches the yield value and correspondingly then afterwards it remains constant until the collapse occurs. But there are different theories which says that many of the things occur simultaneously, therefore one cannot really decide what would be the state of collapse, because in certain stages it says that even when the stress is reaching about 0.87 sigma yp, yielding starts and the failure starts. That is one theory says this. The other theory says if the principal stress is exceeding sigma yp, there is a possibility even then yielding will not start, okay, depending upon the nature of the stresses etc., and whatever theories we have been used. So, those 5 theories what we discussed in the last lectures would be helpful to understand actually the mechanism by which one can get the failure loads or the yield point stresses. Now, what we are interested is those kind of cross sections which are very common for members in marine structures. When they are subjected to combined action of loads, how would the plastic moment carrying capacity of the section gets reduced. So, what we are going to interestingly studying is the PM interaction, that is the bending moment and the axial force interaction. So, you must agree that if you got a beam, a simply supported beam for a span of L, let us say, or let us say I have a fixed beam, of span L subjected to moment, subjected to end moment as well as axial force. I can call this as M and this as N. There will be of course a variation between these ends. Let us say the moment and axial force are acting, you will see that the PM interaction, that is the interaction between the axial force and the bending moment, is very crucial. On the other hand, the bending moment will no more remain M, it will be lesser than M when N is acting. The load carrying capacity in bending is reduced when axial force is also subjected to the section. Alternatively, if the axial force capacity is N, it will be lesser than N when M is acting on the section. On the other hand, when P and M or N and M are interacting together in a given section, there is an influence of one on the other which will reduce the effective load carrying capacity either in bending as well as in axial force. This is what we are going to study today. Now, many members which are commonly used for marine structures are essentially to be checked for buckling effects. So, I should write a statement here, sections that are used for marine sections or marine structures are generally checked for buckling effect. It is because of the simple reason that the thickness proportional to the height or the diameter etc. has to maintain a specific ratio. Now this is handled indirectly by Coates by establishing what we call as a compact limit. Before understanding this, why a buckling effect is to be checked? Because buckling effect is checked because to establish the mode of failure, I should say to establish the mode of failure. The failure can be either by yielding or it can be by buckling. Remember, interestingly, the load at which buckling occurs is much lower than the load at which yielding will occur. Okay. If buckling preludes yielding, you will get the net axial force carrying capacity of the section will be reduced. Okay. So one has got to check the given section or the cross section, is it safe from the buckling effect. International codes which are used for design of marine structures generally advise that buckling effect is indirectly checked by assessing the compact limit of the section. So there is a new term called compact limit. For a given section, if all the members are compact enough, then the buckling effect will not be predominantly acting in this section. So how do you establish a compact section for a compact limit for a given section? If you look at tubular elements, let us say I call this as T and I call this as D. If D by T is less than or equal to E by 9 sigma yp, the section is said to be compact. If the section is compact, then buckling effect can be ignored. That is for the tubular sections. If you look for box sections, these are the common cross sections which are used in marine structures. So we are looking only those sections. Say this is my breadth of the section, this is my depth of the section, be it rectangular. If it is square, both the dimensions can be same, and this is uniform thickness of the section. In this case, B by T and D by T both should be less than or equal to 1.5 times of E by sigma yp root, where E is the Young's modulus of the material where E is modulus of elasticity which is generally 2 10 power 5 for steel, and sigma yp is the yield stress in Newton per mm square. So, if this is established, you can imagine if you are looking for a thickness of let us say 10 millimeter of a box section, no dimension of the section should be less than, let us say for example B by T is said to be equal to 1.5 E by sigma yp, let us say 1.5 into root of 2 10 power 5 by, let us say I take sigma yp for this material as 300. Okay. Let us say for a 10 mm thick 20 mm thick section, breadth cannot be less than or equal to. Okay. So, can you give me what is this value? What is the approximate value of this? Let us say B cannot be less than 175 millimeters. Approximately you can say that the size of the section for a box section of 20 mm thick should start from 200 mm. Okay, that is an idea. If you have a section like that, the section is established to be compact, buckling effects will not be there. You may wonder why buckling effect should not be there, because it reduces the load carrying capacity, and the load at which buckling occurs is much earlier than that of the load at which yielding will occur. Okay, we are talking about plastic capacity, so we are focusing on yielding only. So, the section should not buckle for enable the section to yield. Okay. This is for the box sections. Now, you also have welded box sections. These are common, these are actually used for pipe racks in marine structures. People construct the box section and insert the pipes, conduits inside this, and welded box types are very interesting sections like this. You have upper and lower flange plates, then with that flange plates you create a box section. This is a typical welded box type section. This is what we call technically as an outstand. Okay, let us say this is my breadth of the section, and this dimension is A, and this is thickness of the flange, and this is thickness of the web, and generally it is understood that the outstand, if I call this outstand as let us say B1, B1 generally should not exceed 12 TF. Okay. And of course, this is D, depth of the section. So, the condition is A by TF and D by TW. Should be less than or equal to 1.5 times of E by sigma yp for making the section or confirming the section to be compact. If we talk about the outstand, B2 by Tf should be less than or equal to 0.4 of E by sigma yp. I am not sure, I will check up whether this is whole root or only the root of sigma yp. I will check up this. Okay. So, the section is considered to be compact when this is satisfied. You can also verify this from the quotes whether this is whole of sigma yp or sigma yp. B2 is this. Okay, I will write B1. Outstand. Outstand is B1. So, D standard I sections, where thickness of the web, thickness of the flange, breadth and depth. So, the condition for the section to remain compact is d by Tw should be less than or equal to 1.5 times of E by sigma yp. This is also, I think it should be whole root of E by sigma yp. Let us verify this later. And B by Tf should be equal to 0.8 of E by sigma yp. So, it is important for us to know that how do I establish my section to remain as compact, because compact sections will not have buckling effect acting on them, we can directly deal with the yielding load. Okay, that is why we are discussing this. The next common section, of course, the channel section. Tw, Tf, and let us say this is D and this is T. So, T by Tw is less than E by sigma yp, and B by Tf should be less than 0.4 E by sigma. You can also have a T section. D by Tw 0.4 E by sigma yp, and B by Tf 0.8 by sigma yp. These are all compact limits. Okay, these are all compact limits. These are all compact limits. When these values are satisfied, the section is said to be compact, and the buckling effect on the sections can be ignored in the analysis. You have double angle T's, one more section. Each dimension is B, the overall depth is D, and of course each thickness is Tf. This is web and of course this is the flange. So, this is Tw and this thickness is Tf. In this case, d by Tw should be less than or equal to 0.4 E by sigma yp, and B by Tf is also same relation. So, these are some of the guidelines suggested by the codes based on the geometric composition of different elements, how to establish whether the given section is compact or non-compact. So, I will remove this. So, we reiterate the fact that if the chosen sections satisfies the compact limit, then buckling effect can be ignored. That is the recommendation of the code, okay, can be ignored. Now, let us talk about plastic capacity of sections. So, we spoke about the buckling effect or considering the buckling effect of sections. We said establish something called the compact limit in a given section. If it is satisfied, then buckling effect can be ignored. For of course non-compact sections, buckling effect should be considered in the analysis. Talking about plastic capacity of the section, let us say in both tension and compression, axial capacity, that is plastic load carrying capacity under axial forces, okay, both in tension and compression, is denoted by letter NP. P stands for plastic and N stands for axial, is simply, as we know, is given by A sigma yp, where A is area of the cross section, shear capacity is computed based on the members that contribute to withstand, or I should say resist, shear. You may wonder what do you understand by the term members that contribute to withstand shear. We will see. Let us say I have two cases of an I section. One is kept vertical in elevation, other is kept horizontal, let us say it is tilted. The section is kept like this, it is placed orthogonal to the previous one, and this is my direction of the shear force. This is where my V is acting, that is the direction of the shear force. I call the thickness of the web as S, and I call the overall depth as H. I call this as area of flange 1, this as area of flange 2. This dimension is B in both the cases, and in both the cases this is T. Okay, this is T. And the same section is just rotated. So, the properties or the geometric dimensions or the notations are exactly the same. Okay. What I am interested to compute, the plastic capacity under axial forces. Maybe we have done for axial force, we are now looking for shear. We said that what are those members which will contribute for shear. So, we have got to account for those members. When I got an orientation like this, then the members which do not contribute to shear are the flanges, or on the other hand only the web contributes for shear. Okay. So, flanges take bending and web takes a shear in this orientation, whereas the other way the flanges will now take the shear and this will take the bending. So, depending upon what is the orientation of the section with respect to the force acting direction, we must always either consider or ignore certain members for shear capacity of the sections. So, I can write down here the shear capacity of this section which I say Vp, which is AW into sigma Yp by root 3. What is AW? AW in this example is nothing but H minus 2T into S. Is that okay? That is area of the web alone. Okay, this is 2T, I am writing it deliberately clear. H minus 2T into S, that is area of the web. Okay, this is area. And sigma Yp is of course the yield stress, okay, at plastic stage. Why it is 1 by root over 3? Look at the distortion theory in the last lecture. What is the stress at the minor axis at second and fourth quadrant? There is nothing but 1 over root 3. Okay, you can see that. You can look at the comparative figure which we made in the last lecture. You will see that 1 over root 3 is the value of shear at yield, is it not? Distortion theory. Okay. So, let us look at Vp for this problem. I would obviously ignore now the web and I will consider only the flanges. So, I should say simply AF1 plus AF2 of sigma Yp by root over 3, that is my Vp, whereas AF1 is also equal to AF2 in this case is nothing but B into 2. Okay. So, for shear carrying capacity you must consider only those members which contribute or resist for shear, not all. Okay. Any questions here? Having said this, let us now talk about rectangular sections, and we divide them into two parts or two classifications. One is what we call open sections, other is closed sections. So, we now estimate the torsion capacity. We estimated the axial capacity we estimated the shear capacity, we will now talk about torsion capacity. Okay. So, we divide this into two level of understanding. One is open thin walled sections. I will come to the point what are thin walled sections. Second is closed thin walled sections. The name itself very clearly tell what is thin walled section. The thickness of the section compared to its diameter or the size is very small. In that case we talk this as a thin walled section, what we generally use in members of marine structures. Okay. So, let us talk about an open section for our discussion to compute the torsion capacity, which I call as Tp. T stands for torsion and P is always for the plastic capacity of the section in the whole discussion of this lecture. So, let us say consider a rectangle as shown in the figure 1. I should say as shown in the figure below, because I do not have the numbering of the figure sequentially in this lecture. So, figure shown below, the figure shown below is this. This is my T and let us say this is my B, let us say at any section I look at the shear distribution, because torsion is related to shear. You also know why we say torsion is related to shear. Any idea why torsion is connected to shear? If you look at any Indian courts or international courts, generally if you want to design a section for torsion, we always work out what is called equivalent shear. In design, torsion is always converted or handled as a form of shear. Okay. In Indian courts, for example, IS 456 design of reinforced concrete members, you will always find out whenever a section is subjected to shear and torsion, we find out what is called equivalent shear. Okay. So, the shear will be enhanced by certain amount. There are equations available in the code, that is not the focus here. So, it is always a trend or a method by which torsion is handled in design by the designers. So, we are talking about shear here, I am talking about the shear distribution here. Let us say the section is having a shear distribution as shown here. So, I say this is tau y and this is also tau y. The shear in the extreme fiber is fully same. So, let me pick up the value here and draw a section and say that my shear here in the top fiber is S and the bottom is also S, and this is separated by a distance T by 2, is it not? We understand that when the section is fully stressed, I should say fully plasticized, shear stress will get the value of sigma yp, is it not? We have studied this in the last theories of failure. Okay, sigma yp, it gets the yield value. So, let us say shear force in each direction is given by so S is equal to B into T by 2, that is the area, and the stress of course I am writing here as tau y. The torsional moment now Tp required to balance the shear is given by Tp nothing but S into T by 2, is it not? That is the torsion, that is the moment about this point. So, couple with T by 2. So, that becomes S is B T by 2 tau y of T by 2. So, B T square by 4 tau y is my torsion. Applying the von Mises criteria of shear failure, what is von Mises criteria and failure? Can you tell me what is von Mises criteria of failure? Maximum distortion. So, where what does it shear tau talking about there? What is the maximum value of shear? So, tau y will become equal to sigma yp by root 3, is it not? Is it not? So, therefore, my Tp will now become Bt square by 4 sigma yp by root 3, so on. Why we are talking about distortion theory when we talk about torsion capacity? Any idea? There are many other theories. We can talk about principal stress theory, maximum shear stress theory, strain energy theory, and so on. Why you are talking about the distortion theory here? Because torsion is associated with distortion, is it not? Whenever you apply torsion to a cross section, you will always see the section will get distorted or the fibers will get distorted. That is why you are applying the maximum distortion theory here, and that says it is equal to sigma yp by root 3. So, we have used Tp as this equation. If you really want to apply this concept for a I section, the same concept can be applied as it is. Tp will be now sum of I, let us say Bi Ti square by 4 sigma yp by root, where I is the summation of number of rectangles in the I section. So, if you have an I section, so I can say Tp using this expression, this is B, these are all T, this is also T, this is also T, and this is H. Okay. So, sigma yp by root 3 into 1 by 4 is common, Bt into 2, there are 2 Bt's, plus H minus 2T of T. And that square, sorry, let us say b t square, because there is b t square in the equation, okay, b t square of 2, because there are 2 elements here, and this is h minus 2 t of t square. Is that okay? This will give me the torsion capacity directly. This for open sections. Talk about now for closed sections. Let us say the ring has uniform thickness T, and of course the diameter of the ring is T, and the center there is torsion applied which is Tp. Let us look at this and try to look at the distribution. Any one specific level, let us say okay, that is the force which is acting on the level, and I call this as my tau y. So we are talking about thin walled sections where we say T is much lower than D, okay, please understand that we are talking about thin walled sections. So in the plastic range, the shear stress value equals to sigma yp throughout the thickness of the section. That is an assumption or reality. This is true because we are talking about the thickness very less than the diameter of the section, thin walled section. So the thickness is uniformly plasticized for a whole value of T. There is no question of partial plastic and partial elastic core lying within the thickness, okay. It is fully plasticized, full thickness is having tau y, okay, that is the statement. Then the torsion capacity is given by Tp is pi dt, pi d is the circumferential length and T is the thickness, so that gives me area multiplied by tau y will give me the force and moment d by 2, is it not? I am talking about the stress values here, this is d by 2, I am taking moment about the center, is it not? Torsion is about the center, d by 2. So this is, I can call this equation number, I do not remember the sequence, let it be 4, is that okay? 4, okay. So pi d square by 2 t tau y. So applying von Mises failure criterion, Tp can be said as pi d square by 2 T sigma yp by root 3, that is what von Mises stresses say. I can also call this as 2 at sigma yp by root 3 because A is pi d square by 4, is it not? So, for closed sections you get torsion capacity like this. Okay. So, in this lecture we discussed about how to estimate the torsion capacity for different sections, open and closed, for different standard cross sections in geometry being used as members in marine structures. What would be the necessity of studying a buckling effect, because then we eliminate the buckling effect if the section is declared as compact section or compact limit is proved or established, which is given by the expressions and equations as we discussed in the lecture. In the next lecture we will talk about what would be the plastic moment carrying capacity, plastic capacity of the sections under the combined action of shear, axial, shear, bending, shear, torsion, etc. Combined effect of these forces in the next lecture.